In MCQ 12, this is a chemical energetics question that encourages students to remember the different definition of standard enthalpy changes. So we have delta H1, delta H2, delta H3 as well as delta H4 in this question. Let's investigate to see which of this do they actually represent. So starting off with delta H1, you do see that I have my C6H12 reacting with oxygen to give us carbon dioxide as well as H2O. So this is very reminiscent of the combustion of C6H12. Now, however, I am very reluctant to put a Tito symbol over here. It's because to be at a Tito symbol, this has to be at standard condition. And standard condition is conducted at 25 degrees Celsius as well as 180. And the reason why the reluctance actually sets in have to do largely with the state symbol of water. Because if it's at standard condition at 25 degrees Celsius, water has to be at the liquid state symbol rather than the gaseous state symbol. So I will just say that for delta H1, it's just your enthalpy combustion of C6H12 without the word standard. And this is why option A is actually wrong, because the Tito symbol was actually being placed there. That is not going to be agreeable with the state symbol of water. Now looking at delta H2, this itself started with monoatomic carbon, solid, diatomic hydrogen gas and diatomic oxygen gas. These are all the elements at its most stable state. And based off this, you can see that this portion over here are the makeup of C6H12. And since these are elements at its most stable state, this is considered to be enthalpy formation of C6H12 plus the enthalpy formation of O2. Now this portion here is considered to be redundant simply because for the case of elements itself, enthalpy formation of elements is always equal to 0. So actually this part, whether I put it or not, it doesn't really matter. So enthalpy H2 is the standard enthalpy formation of my C6H12. And with the state symbol of liquid, so B seems to be the correct answer at this particular moment. Let's just take a look to see whether option C and D are they wrong to support the fact that option B is actually correct. So take a look at delta H3. You do see that we do have carbon, we have 12H as well as 9O2. So to move from the changes of 6H2 towards 12H, this could be seen as the enthalpy atomization of hydrogen multiplied by 12. That's because for every atomization, you end up with one gaseous atom. So if I'm going to have 12 hydrogen atoms, this will be representative of 12 times my standard enthalpy atomization of hydrogen. Now, however, if I'm going to use data booklet, this could also be determined by taking the bond energy of my diatomic hydrogen multiply by 6. Now, if I'm going to overcome 6 diatomic hydrogen, I will similarly end up with 12 gaseous hydrogen. So if you take a look at part C, they mentioned this is 6 times atomization of H2. So this is going to be wrong because definition here suggests that for each atomization, you end up with 1 mole of gaseous atom. And as mentioned, if let's say it was 12 moles of gaseous atoms of hydrogen that was being formed, that must have meant that instead of 6, we should be looking at 12. So everyone, this is where the definition becomes very, very imperative for you to understand styles of questions like this. Now in the last set over here, we're looking for delta H4. So in delta H4, we do have 12 hydrogen, alright? Actually, together with 6 of your carbon, is for you to form your CO2 as well as to form your H2O. So at first glance, it could be seen as a form of enthalpy formation. However, my 12H, this is not how hydrogen exists at standard condition. So if you're going to use it for formation at standard condition, it should rather exist as diatomic hydrogen gas. So this is already an issue over here to suggest that it cannot be used for the formation of H2O, because for the formation of H2O, the equation should have been H2 plus O2 to give us H2O, and we're just going to balance with a half over here. So instead of using H2, the question was actually using 12H. So this is not how the element exists at standard condition. So definitely for delta H4, I would say that this portion is really out by itself already, and this is wrong. Now, however, when it comes to the fact of carbon dioxide, there is still some merit in this, because for carbon dioxide formation, we're going to have carbon plus oxygen to give us CO2. And since we're in the interest of making 6 carbon dioxide, we will need a total of 6 carbon, which is seen over here, and we will only need 6 out of the 9 oxygen that was actually available. So I'll say yes, this can be represented as the formation of CO2, but it cannot be represented as the formation of H2. So this means that the correct answer for this question once again is going to be option B.